Hello, everybody. How are you doing?
Hey, Professor Gwen, how are you doing today?
I'm okay, thank you. It's been a crazy day. My class, my students, they want to compete in the cybersecurity competition this Saturday, so trying to coordinate things and get my team ready. But yeah, we have a couple competition.
That's
Hi. Yeah. So
Gwen, can I ask you a quick question?
sure.
I know I'm like 2 days late on turning in the homework assignment. I'm stuck on question one. Do you know what is the answer to the question one? The two blank questions.
Okay, give me 1 second. Let
Yeah.
me get my folders open, okay?
No problem.
I had moved my stuff to D drive because my C drive is very small. Okay, that was last week, unit 3.
No, it was the homework assignment for the quiz review.
Oh, the homework assignment. Okay.
I spent like the last 12 hours trying to find the answer to this one. Needless to say, I
Okay.
studied a lot.
The blank is the legitimate representation of the operand, such as that the computer can perform operations on the representation. What do you think that is? What do you think that could be? So when we talk
I
about,
think computer language or machine language or learning.
so before it becomes machine language, what does it need?
Instructions.
Yes. Right? Yes, that's it.
So an instruction.
Mm-hmm.
All right. Yeah, maybe I was overthinking it. Thank you.
Yeah. And then you said this the second question.
Oh no, I got the second
right?
one.
Oh,
Yeah.
okay. Okay.
Yeah.
All right.
Yeah. Thanks.
Yeah, I just the verbiage on that question, I think I pulled that directly from the chapter. So
Okay.
yeah. Hi everyone. Thanks for joining this evening. We are gonna go over Unit 4. Yay, we're moving along. So let's get your notes open and your assignment open. We are looking at chapter 5 notes. So we're gonna go a little deeper. I did receive a few questions via email about, the confusion in moving data like load and LDI, and then we're gonna talk about LDR. So hopefully this session is gonna clear it up for you. And then it's gonna give you like a better picture on how you would use these instructions or your LC3. Okay, so let me get my assignment open as well. I did modify this compared to what it was last year because as I look at what the students need, I adjust the assignment. So it is 6 o'clock now, and so let me turn on my caption so I don't forget. And that will get me the file. And also, I will share my screen. So before we look at the assignment, let's take a look at the notes. Okay. So in this week, we are gonna look at some of the specific instructions. We're gonna review some of the concept that we talked about last week, along with clarifying some of the areas that might cause any kind of confusion for you when you're working with LC3. And as you are programming in LC3, and if you do like it, I suggest that you can look at assembly programming jobs. There are a lot of jobs that will give you, not in LC3. LC3 is used for teaching and learning, but as you use LC3, when you read ARM program or another language, it's going to look very familiar to you. It's like learning C++, and you'll be able to understand C or learning C and then be able to write in C++. So there are going to be very similar instructions, and it's going to use add and sometime additional operations. Okay. So this week we're going to talk about your instruction set architecture, ISA. And ISA is a way that we can specify how memory and registers and instructions and opcodes are used. So this is what you visibly see when you're looking at your simulator and after you write your code, like what we talked about since we started doing the lab with LC3, right? Your origination address, you see where your program starts and how you would use your memory addresses in various locations for your label, and then moving some of that into the register, which is temporary memory, and how to be able to work with data. So now in C++, we normally would have data type, right? Like int, double, long, float, etc. Considering the type of data that you're using, so far we've been really working with smaller numbers, but we will expand this to arrays and something that would require a larger memory location down the line. So you will see that in the lab, so you will know how to be able to use it. So ISA gives you, right, the overall aspect of what you would see on the low level. It gives you all the information that you would need to be able to write a program for the machine language. Okay. Now, coming back to what we talked about before as the word size in this class, our word size is going to be 16 bits. And so since data is stored in binary in the computer, we would have 2 to the 16 power, and that would give you approximately 65,000 locations. But keep in mind that we are not using all the entire set of addresses that would be for 2 to the 16 power. Okay. Now, in the last week, we talked about memory space and the address for those memory space, and we did the calculation in that. But in this class, so every time that you would have a line in your code, right? Like let's say that I want to clear register, I would say and R1, right? R10. Basically that takes up one word. Okay, so when it puts it into the machine, after you assemble it and you load it, what you would see is that line specifically take up 16 bits, right? So it's going to increment accordingly. So if your program is 100 lines, right, we start at hex 3000, it's going to subsequently add that. And once in a while, we also need to move back and forth in the memory location, and you see some of this when we're incrementing in loops, when we are, going, we can jump, we can control the flow where we would go to a specific location in the memory in order to operate. Now, register is only going to handle things temporarily. It doesn't have all the data that you would require to retain. So we touched on that last time. So the register sets, register 0 through 7, those are your general register. And as we say that this would be your temporary storage. If your current instruction, if you want to operate your current instruction, you have to use the register in order to do that. There are times that we would load data from the location, and then there are times that we would load data from a register. So this is why when we are using certain load and store, we are specific in that sometimes we can skip the PC, which is the pointer to your counter for the processor. Sometimes we would use, a regular load where we would pull that from memory. So your register is going to be the middleman that's going to be in charge of all how you want to access, right, your data or do something, have some kind of operation perform on the data. Now the number here, it talks about how the register would have the same property as your memory locations that's used to store. And the easiest way to think about register is that they're like temporary file, right? That will be considered as a memory space, but that dedicated memory space is temporary. And the number that is stored, that will be in bits, or we would refer to that as our line of instruction would take up 16 bits or 1 word. And in the case where we need to use larger size, we would then use multiple block words, or we would be able to increment the space that we need to represent an array or a location where we can store a group of data. So the below just shows you a little bit of like the 2D illustration on how the registers would be, right? Sometimes we would have different values there depending on your instructions. All right, so with that said, let me flip to your assignment. So in the how many locations can be addressed in LC3? In LC3, we are using 16-bit word size, so that will be 2 to the 60. In the case where if you have 32-bit word size or even larger, right? And that will take it from 2, we would take 2 and raise it to the power of 32, if it's 32-bit, and so on. So that would give you the locations, the number of locations. And now keep in mind that we're not using everything, right? There's some space that's going to be reserved. So in that, right, for the majority of the longer programs, we should be able to execute the longer program as we don't exceed that entire set of space or the group of addresses that's allowed. So how many bits are used per address location? So every time that you look at your simulator, right, each of the address line, right, that takes up 16 bits. So when you load your program, you originated at hex 3000, and the first line of your code, let's say that I do an LEA with the label, right, LEA R0 label 1, that takes up 16 bits, and that would start at the hex 3000, which is the address in the memory. And then the next line would be the next 16 bits, and so on. So if you have 100 lines later, it's going to go all the way down. So when we think about how we would set up the fill, right, if your program is very long, like I said in the last week, you want to go, maybe if it's 100 line, then you want to go a little bit further for your fill, so that way it's not overlapping in that space throughout your program. Okay, so what you would see is that per address, that's going to give you 16 bits. Any question with this? And we have worked with registers. The registers that we normally use are going to be registers 0 through 7. And we learn in doing some of the labs that register 0 is usually used for input and output. That's the first register. So anytime that you need to do input output, you're going to make sure that you're using register 0. And in the last lab, you start seeing, in the last lecture, we start talking about jump and also branching. And you started to see how register 7, which is the last one in the set, is used for specific pseudo instruction or instruction. So here, so keep in mind that how you using and reusing registers, and some of the registers are dedicated for specific things, right? So your general purpose registers for number 3, that would be register 0 through 7. Any questions regarding just the basic? This is also review from the prior weeks as well. Okay, so before I go over the next one, let's come back to here. Okay, and in the next part, it talks about an instruction. So an instruction is made of 2 components, and that's important. Your opcode, which is where you would be add and, right? You would write the add, the and, the not, jump, the branch. So that will be your opcode. That takes up the first 4 bits. And then in following that, that will be your operands. That could be another register, or memory location, which is tied to a label, a value. Okay. So we want to, depending on what you would have as an opcode, that will follow with the appropriate operands. So the example here, we would see that we are adding, right, R0, whatever is in that R0, in the register 0, with the hex 1. So this is how we can bring in 1, and we would initialize that for R0. And then we put it back into R0. So with that, we would R0 stores 1, right? Assuming that there's no prior value that's in there. Okay. So we mentioned that ISA is a way that we can define opcodes, data types, addressing modes, and the addressing modes are determined by how you're using the operands and where they're located. Okay, so in the case where if we're using a label and we can tie that label to an address by using a fill. So in the machine, it takes that fill as a value and it puts it, right, to the label. But as you set the value, the simulator, you would jump to that location, right? And you would set the value to that location. So that's how we can associate a space to a name, which is an identifier, like how you would be with a variable, and by doing a fill in assembly. And you see this with Microsoft ASM, NASM, and other assembly languages as well, same concept. Okay. So there are 15 instructions, and these are going to be specific opcodes. So at the low level, right, when people design the processor, the developers, the engineers, they would need to set up the number of bits that would be for the instruction or the opcode. Then it would be specified to a certain operation. So for example, add is equivalent to, you know, certain 0 and 1s. So LC3 only have 15 instructions compared to other assembly language, you might have more. Okay. Some, like I said before, would require rotate for rotation, and then, you know, OR and additional things, but LC3 doesn't use OR. So your opcode is going to be the front 4 bits, so bit 15 to bit 12 to bit 15, and the operands will follow. Okay. So since we're using 4 bits, there would be 16 distinct opcodes that's possible, right? So 2 to the 4th power, that's going to give you 16 distinct opcodes, but LC3 is only going to use 15, so it doesn't max out with 16. Okay. Now, the 0 and 1s in the opcode section, that would specify what the machine would need to do, right? Add or not, or etc. So you would have the first 4 bits that would specify the exact opcode that it needs to perform. Okay. So there are 3 categories of instructions. You would have operate instructions that would require processing information. You would have data movement. We talked about load in different forms. This is the way that we would move, right? Or we can bring in data, and then we can take that data and store it using the store instruction to a certain location. So at the low level, we're really moving things around, take the value or the data and do something with that, do some calculation in the computation. So the computer calculates, and that's what it does, right? It adds. Then we have the control instructions in how we would use loop. And in our case, we would use branch right? -0 and positive. So we can change the sequence of our program by jumping by branching. And for our data type, this is going to be represented in how the data would be in your memory location. And we would normally work with hexadecimal, in some cases with decimal. So the opcode is going to operate on your data. Now, if you're using integers, you simply is just going to bring in the value and be able to initialize that value to a label, like what we've been doing in the lab. Okay, any question? Okay, so for how it asks you how are the registers identified in the LC3? So LC3, the way that it's designed is that you would have a 3-bit register number, right? So after the opcode, right, the next part after that, so let's say if I have, for example, my instruction again is I can add, right, R0, and a hex 1. So this takes up the 4 bits in the front already, right, 15 to 12. And the next 3 bits are going to be dedicated to the destination register. Okay, so how does it know which register? So if it's represented by 0 like this, that will be your register 0. Okay, if it's 001 like this, it will know that it's register 1. So it's really simple, and you simply convert, right, binary to hexadecimal equivalent, and 010 that will be register 2, and then 011 that will be register 3, and so on. And so at the 3 bits, we're able to represent all 8 registers starting with register 0. So the add is represented in binaries, right? And then the registers is also represented in binary, and so on. So that's how it's able to see, right, all of what you write in instructions at the binary level. And we'll do an exercise with this, or a few exercises with this.
Does this cycle go all the way through to R7?
Yes. So if you do a binary conversion, what would be R7? 1,
1, right?
1, and 1. Yeah, all 1. Okay. So for register 7, right, that's at the end. So we can represent this, right, because it's 1, 2, 4. So your register 7 would be, right, equal to 111. Because if you convert the binary for that, you would have register 7. So when you simulate and you're looking at the binary, it would be exactly what would be equivalent in your LC3 instruction. Okay, this is why the simulator, when you look at that line, you would see what that means in binary, and then next to that, that will be your instruction, like add R0, X1. So pay attention to that the next time you use your simulator in our lab. Okay, for the next question, and I think we touch on this in the notes. What would consist of an instruction? Your opcode and operands. Those are the 2 major components. Opcode, what we're doing, right? And then operands, what are we doing it to, right? Your registers and values, or register and label. So the opcode really helps us determine what will be following, right? You're always going to have a destination register, but then following that, whatever, depending on your opcode, that's what's going to be here for your operands. Then we touch on how many total instructions. So 2 to the 4th give us 16, but we're only using 15 in LC3. So there are a total of 15 instructions. And you can refer to your notes for the details in that. I did take some of the content from the slides that came with the book, and I added some things to it just to have it one centralized document. Now for question 7, it asks you to identify and explain the purpose of the LC3 opcode types. And we said that there are 3 categories, and you can find this in the notes. We want to operate, so operate operational instructions. Okay. Okay, so the difference between add and AND. So when you use binary, if you're AND, right, it's you using the operator AND. When you're add, you're simply adding a value like addition. Okay. In the first week, we spent time looking at how to do binary addition. So it would use the addition operation when you're doing an add. Okay. So going back to this example, if I'm adding, right? So let's say that I have 0, nothing here and nothing here and a 1, right? So what I'm doing is it's like this. 2, 4, 6, 7, 8. And then I'm going to plus it with that. Okay, so if I have nothing in my register 0, that will be 0, right? It's nothing. And then I would add a hex 1, which is equivalent to a decimal 1. It will be like this. But when you're ANDing, right? R0, R0, right? Let's say we would AND it with the 1 again. Okay. Assuming that we would have nothing in the first part, in the register 0, and then if we AND it with a hex 1 or a decimal 1, when you AND, right? So when you AND 0 with a 1, you get a 0. So the result is different. Okay. And that comes back to our first lesson for this class. Are we clear on this? Any question? So it is different in that this is an operator and this is addition. Okay. All right. Just a quick example. Okay. So going back to 7, we said that we want to operate, right? So we would have operational instructions that will be process information, or usually that's just calculation, like add. We would have data movement that will be your load and store. Okay, different form of loads and different form of store, like LD, LDI, LEA, LDR, and then the store ST, STI, STR. And then control instructions, we talked about jump and branch. So you would be able to change the sequence of instructions. We can jump to a label similar to what you've seen with go to, and I explained go to, how that's different than in C compared to assembly when you do a jump. And then when you branch, right, we would see that equivalent to C++ if, else statement, or loop. So you can jump to a location, you can branch to a location by label. And we did a lab on this last time. We will do more. So this is verbatim from your notes, so you can pull that from your notes as well. Then for question 8, it asks you, where can an operand be found? It would be in your memory, in registers, or as part of the instruction, which is a location in memory. So register is a form of memory, it's just temporary, right? Where when we use memory, like with the label, that's RAM. Okay, so this is a way that we can identify a certain value, right? You can point to a location, like when you're using pointer in C++, that's in memory. But when you are, let's say, calling a function, it gotta push that onto a stack in C++, right? Then that in the machine level, it's actually using the register in order to operate that. Okay. So when you do function calls, or when you passing, you overloading of functions, etc. in C, C++, you're really using the register, right, at the machine level. And also memory locations, because if your variables or your arrays is initialized, that's how it's going to be able to retrieve the data. But it needs to bring that into the register so it can operate or process. That's what we would say. Okay. Any question with 8? Okay, so here it talks about address mode. So addressing mode, we would need to be able to specify, right, the operand where that's located. So if my operand is a label like a string, like str1, okay, we need to specify what that is and where it's located. Okay, so that way the register, we can load this into the register and we will be able to output. So label is in a memory location. We're able to load it to the register so we can out. Okay. Puts. Now the operands, as you can find the answer there, it tells you that it's in memory register or part of the instructions. If the operand is part of the instructions, this is when you hear this in programming classes, right? These are going to be immediate values or literal values. Okay. So after you initialize the value, right, that would be represented as the literal or the immediate operand. Because in order to initialize that value, so for example, int variable 1 is 9, right? That value needs to be part of the instructions at the machine level. So we have to say, right, we gotta bring that into the register so that way it can be used or associated with the label, the variable. So there are 3 types of modes, and you're gonna hear this throughout, the concept lectures of this class: PC relative, indirect, and base offset. And so when you see PC relative, remember we define what PC is, right? That will be the counter for what processes. So it's a way to point to which process is current and next. And then you would have an indirect that is not PC relative, and base offset. So the last 2 really utilize memory locations. Now, your conditional codes, we would see this with conditional statement that we write in C++, like how we would use branching. So when we branch, we simply look at the value in the register. If that value is negative, we can send it to a location, or we can branch it for 0 or positive. Can you branch multiple? Sure. So you often see that you can use like comparison operator, right? Like X is greater or equal to 5. Okay. So we can combine these flags to be able to implement what we would see as a compound comparison operator. Like greater or equal to, less than or equal to. Because as you subtract, right? Let's say if I say X is greater or equal to 0, as you subtract, it could be 0, it could be positive. So I can use BRnzp. But if I say X is less than or equal to 0, I can branch it for negative and 0, because as I subtract, I can have a 0 where it would be equal to 0, or less than, that will be -1, -2, -3, and so on. So that will be N. Okay. So this is part of the conditional codes. Now, here again, it talks about the 3 single-bit registers that will be referred to your conditional code. So it uses what's inside the register in the previous line to verify the condition to meet whether Z, P, and N. And this has to be intentional when you program, right? If you want to set up a conditional statement, you gotta make sure that before you branch, whatever the value in that register at that line, right, before you branch, it can be verified for the -0 and positive or positive. Okay, so we have to be intentional in that area. And I didn't emphasize this in the prior semester, so it took the students a little longer to kind of grasp like the branching. But as you also practice this, you want to pay attention to, oh, at the branch or right before the branch, what number am I looking at, right? What is the value at that line before? What is it checking for the true or false there? Okay. Okay. So now for the operation or operate instructions, we would see add, and not. Those are the 3 in LC3. Now in other assembly language, you would see or. Okay. I know Microsoft ASM, you can subtract. So basically it does the 2 complement. So, you know, that's just, it combined like, you know, the add and the not in one instruction. So the opcode for LC3, we only need to know these. For the operation, you can add and not. And how does it know when to do the not compared to the other? The bits are different for the first 4. So when you use a not, we would have a 1001. And this is a unary, so it doesn't require 2 input. There's only 1 input. Okay. So when you saw when we did the subtraction for the last couple of weeks, right, we would not, for example, not R1, R1. So there are only 2 pieces, like the destination register and the operand or the source register. Now for the add, it would be 0001 in the front. And then for the and, it's 0101. So that's how it can distinguish between add and not. Okay, for the opcode bits, they are different. Any question? Okay, so let's come back to here. So we already talked about the 5 address modes, right? So you have the immediate, which is the literal for number 9, the register, the PC relative, the indirect, and the base offset. Those are your 5 addressing modes. So we can have a fill, right? We can put a value to the register. We can use the PC relative mode with the load, and we can do an LDI with the label. Okay. Now for 10, we just answered this. So describe how NZP registers are used in the general purpose register. So these are also the registers for the branch. Okay. So N stands for negative. If the result is negative, the N register is set and the 0 and the positive is cleared. Okay, so it will turn this on. So that's how it's able to understand that the value is negative. For the 0, if that Z is for 0, if your result is 0, the Z is turned on and the N and the P are cleared. And then for the P, that will be positive. If the result is positive, P is set and the N and the Z are cleared. Okay, so it's simply looking at, right, that those register when it branch. Now, if I combine them, like I said, like we can have the N and the Z combined. So those two are on and then the P is off or it's cleared. So that's how it's able to distinguish, right, how to branch or negative, 0, and positive. Question? Okay, for 11, it's really simple. You can use any of the operate instructions. So I always use the clear because that's normally what we do when we start our program. We want to clear out some register. So when you AND anything with a 0, it becomes a 0. So you initialize that register to 0. So you can use an AND, or, you know, you don't have to write all of them, but another way, another operate instruction we can add. So in this case, we add a decimal 7 to register 0 and then store it back to register 0. So we put the result in register 0. So it's like saying register 0 is decimal 7. Or we can add 2 to register 1. And then if once we have register 0 and register 1 initialized at 7 and 2, we can add them together and put it in another register. So register 3 now have 9. Okay. So if you want to bring in a value to a register, you add. Okay. Can I load it? I sure can with the fill to the label. You've seen this when we did the ASCII conversion in our first lab. So you can also bring in a hex value or a number, right? But you would tie it to a label and then you can load it. Okay. But if you just simply want to have an integers, just an integer for some kind of operation, yeah, you can add. That's the easiest. one line. Now there's limitation in this. Last week I said that when you look at the notes later on, it shows that there's the 5 bits that's going to be used for this value. So in a larger number, you're going to exceed that 5 bits, right? So let's say that if I want to add the decimal 9,000, it's going to exceed the 5 bits. So I can add it in increments in multiple lines, or then I have to come back and think about how I would fill to be able to bring in that value to the register. Okay. So any of these are okay. You can also come up with your own.
Professor, I had a quick question. If we needed to subtract, I understand we would use a not, but I'm just curious, what is the order of the registers to subtract? Like, are we subtracting R1 or adding R1 to R0, or like what, or is it the reverse way?
So let's say that, let's clear this out, right? Oh. Let's do, let me come back. Let's go to, let's make this subtract, okay? So let's say if I wanted to subtract 7 to 7 minus 2, right? That's my goal, 7 minus 2, right? So here, I know that 7 is at register 0 and 2 is at register 1. So what I need is I need to combine them together. So first I got a not, right? R1, right? That makes it 1's complement. Okay. Then I need to do a add R1, and let's do a decimal 1. Okay. So here I would have R1 is equal to -2, right? And then if I want to take 7 and subtract it, I would do this next line. So let's say that I want to put the result, which is 5, on register 1. That's my destination register. And what am I subtracting? The value is 7 to 2, right? So where's 7? Register 0. So that will be your source. Okay. What's next? R1, right? Because R1 is -2. Understand? So here is 7. Here is 2. I'm taking 7 and I'm subtracting 2. So it doesn't matter because we're adding. Can I have it in reverse? It's still going to give you the same result. It's like taking -2 plus 7.
Yeah, I see it. Thank you.
Okay, yeah. So here you have R1 is your decimal 5. So the cool thing is that if we add, right, doesn't matter because we already have the 2's complement, which is -2. So if you take -2 plus 7, is it the same as 7 plus -2? Yeah, it's the same. Good question. Sometimes that gets confusing because you're like, oh, which order? You know, as long as you understand that this is the destination where it stores result, right? The back is really how you think of the order. And for me, I always keep it in order. So I know like this, subtract this. So because as you move along in a longer program, you want to track your register, right? And be able to follow like, at this line, it's equal to this, and at this line, it's equal to this. So otherwise, you know, and you have to go back and fix some of the error in case you run into error. Okay, so you got to track your register and value. Okay, so let's do, let's take a look at the notes again, and before we do the next part. Okay, so we talked about the add, and the add have 001 in the front, and then your register, and then your register 4. So what we're going to do in number 12 is we are going to take, right, the instruction and we're going to break it down to the binary level. Okay. And so that way you can see what the computer is seeing. And that's the purpose of this class, is to really see, right, like how data is moved, right? How it's processing that, what kind of 0 and 1s is it doing? Because when you understand that, right, it ties together all the things that you've been learning in programming in other classes. Okay. So when we talked about not, it's a unary. So when you add, right, what happens is there are a few things. You're going to have the destination registers, which is whichever register you want to put it in. For in our case just now, right, R1. That's where it's going to store the result. Then it has two separate files. You got your source register, source 1 and source 2. And so when you're looking at the 16 bits, the first 4 bits is for the add. So it would be 0, 0, 0, 1. Then the next 3 bit is your destination register, right? That could be from R0 to R7, any of the register that you select there. And then after that, your source register, okay? So when we're subtracting or adding the negative, right, your source was where it stores the 7, and then the second source was for the -2, right? So here is where it would use this for branching purposes. So in the case where you would have like, so this would 0 out for, that means it's their register mode. Okay. So that would be your register mode. So that will be an add. Now, if you want to add the example that we had, right? When we add a value, that's called the immediate value. So when it adds register to register, this bit right here is 0. Okay. But when you add a value like a hex 4 or a decimal 7 or something like this, which is too large, right? It's going to overflow. So then this is going to become a 1. So that way it knows that it's a literal or an immediate value. It's called the immediate mode when that's set to 1. Okay. Then the value that goes next is going to be here, right? So your hex 4 needs to fit into this 5 bits. Or the next number needs to fit into this 5 bits. So why did I say that this is too large and it's going to overflow? Well, a hex value is equivalent to 4 bits. And the next value is equivalent to another 4 bits. So alone, 7A is already taken up 8 bits. So it will not fit this whole entire thing. It will fit like A. Okay, so when you do this in the code, it's going to throw an error because it cannot fit all of these digits onto these 5 bits. So when you're trying to do an add with a value, an immediate value, like a hex or a decimal, think about the 5 bits at the end. And this is why I put that at the notes for the lab last time, that when you're doing like a hex D4, right? Hex D4 is 8 bits. It will not fit one add. Okay. So when you do, when you add a hex value, it will fit here, but 2 hex digits will not fit here. Okay, because they're only 5 bits. Okay, any question?
So for that add for when you're adding hex, do you add like one hex digit and then another add for another hex digit separately, and then it comes out like the way you want it to?
Yeah. So you have to intentionally use the add like multiple times. Okay. So if I need to add this value, right, I have to break it down into multiple lines. Or easier way is we would load with a fill. So I can fill a label with this and then load that label to the register. Done, right? 2 lines. Okay. So when you have a larger value, it is more beneficial to associate that to the memory because it's larger data. And So what they're saying is on your register, it's really designed to use smaller pieces of data as in, or smaller value as immediate or literal. Okay. So when you think about that in C or C++, right, this ties to your data type. Okay. So in the larger type, where it would use, it would require more space, it makes more sense to really put that on the memory and then go and fetch it. Okay. Versus where if we initialize it at the register for use for operation, we would chunk it into the smaller pieces, because, the intention, I think, is really, with the larger data set, because of the word size, it's very limited in how it would use, a certain number of bits for larger data. So if we're only dedicating 5 bits, right? If you do the math for that, when you do the conversion from binary to decimal, you're limited to the values that you can add here.
Okay.
Yeah. Now, on other type of assembly language where it is a larger word size, you're able to, you can do more with that. So that's why they would have more instructions and, more space basically to really use for data. Okay. But if you understand this, right, this is the foundation. So if you understand this, when you look at other languages, it makes sense. Okay, it's going to be like, oh, okay, the only difference is that they're using this for, for other type of values.
Okay.
Oh, okay. Other questions? Okay, so let's look at how things are at, right? So when you deal with operation, your arithmetic logic unit is at work. Okay. So here your register, okay, needs to look at how things are going to be. Is it sign extended? And your source and destination register, right? So your source register is going to go into the ALU. Your instructions is going to go into the ALU because we're operating. And then when after it adds, it's going to put it into your destination register file. Okay, so simply whatever value that you have in the source, let's say in our case, a 1 or a 0 or a 4, whatever that you had previously had initialized, that's going to put it into the ALU, and that's how it's able to operate. Or if you're using a NOT, that's the same thing. Okay, it uses the ALU, arithmetic logic unit, so it calculates. For your data movement, these are your data movement instructions. LD stands for load direct. LDR stands for load register. LDI stands for load indirect. LEA stands for load effective address. ST is store. STR is store to register, and STI is store indirect. Okay, these are the 7 instructions for data movement. So when we load and store, we use label. Okay, you can load to register, but rarely the case, because our program really, we want to have some permanent result at the end. So we often use LD, LDI, and LEA, and ST and STI more. Okay, so you will see that throughout your labs. Okay, so similar to what you've seen in the other instructions, your opcode, the first front, the 15 bit 12 to bit 15, and then your destination register. Okay, and then or your destination register. If you're doing an LDR, there also is a source register. But because we're using label with store and load, the rest of this from bit 0 to bit 8, that's dedicated to address for your label. Okay, what you fill in your label, that's going to put it there. Okay. Okay, so let's break this down now. Right, this is the confusing part before we do this. So load, we say that you'll read your data from the memory to the register. Okay, from the memory to the register. So you would load to the register. Anytime you load, you bring in to the register. Now at the end, if you load at the beginning, at the end you have to store because you got to put it back into the memory. So you would write the data to the memory. Sometimes we would store first, then you have to load at the end. Okay, they always go together. Okay, so if you do an LD at the beginning, you would do an ST at the end, vice versa. If you do an LDI at the beginning, you have to do an STI at the end. Okay, practice. Okay, so for LEA, we would use this with string. Okay, so the difference between LD and LDI in that LD is a PC relative mode. It uses the program counter. So it has to increment the 1 right after it loads because it needs to get ready for the next instructions. Compared to the LDI, it uses the indirect. Okay, it is not PC relative. And I will give you some examples shortly. Same with ST and STI. For the LDR and the STR, we use this with the base offset mode, and that I think we have one lab that touches on this, but you can do this with registers to registers. Okay. All right. So how does it know when you load? If you do an LD, your opcode is load, that will be 0010. And for the store, it's 0011. These two are PC relative addressing mode. Okay. And that will be your 0 to bit 8. That will be your address. So what it does is the instructions specify the offset relative to the program counter. The memory would be computed. So how you fill your label, that value is computed and it would bring that to the PC counter. So that way it would know. Okay. And it's going to add the result and it's going to increment the PC. It has to do a +1 to go to the next instruction, to point to the next instruction. So if you think about like how the address is, the location, right? It computes it, it adds it, and then it needs to go to the next piece. So it drops down in the next address to be able to use to execute or to put the next instruction to become the current for the next part as it flows down in your code. Okay. And we talked about the different phases last time. So here it explains that the incremented PC, the content of that, after it fetch it, it needs to be incremented. So the memory location corresponding to the address is read. Okay, because if it doesn't, it will not get to that space to read whatever the value and the operation that you want to do. Okay. Now, if you specify the address directly into the instruction, if we're using an address and it is 16-bit, after it takes out the opcode, and the register, which is already 7 bits, you have the remaining bits for your addresses. Okay, so that would be the 4 bits for the opcode and the 3 bits for the register, you would have the 9 bits that will be available for the addresses. So it needs to fit it there. But how can we have all of these other addresses as we are 16-bit word size, right? So to fix that, what they would use is for the 9 bits, that would be, oh, I didn't include that. That will be 2 to the 9th. So it would be sign offset for the current PC. Okay. So that means that we only have 9 bits for what would be the available addresses. So we're not, that's why we're not using, right, all of the addresses. That's what they said at the beginning. Okay, so now let's say that you doing a load. Okay, let's say that I want to load this label var1 to register 2. I simply do a load register 2 var1. Okay. And similarly, we can also do an LDI, right? But let's say that we do a load for this. Okay. So what that means is it's going to be the opcode here, 0010. The destination, that will be your registers 2. So that will be 0, right? 10. And then the rest of this, like we said, the 9 bits is going to be PC offset. So when they say PC offset 9, that simply is the address of your label, your fill. Okay. So if you look at this diagram, okay, the PC is going to be incremented because this is the PC relative. Okay. And the address is going to go into the MAR. Okay. The source register is going to contain the data, which is where it's going to load into the MDR. And that data is then going to be put into the memory. So when it is PC relative, it goes through the ALU, but it needs to increment. And after it increments, right, it adds that, it's going to put it into the memory address register. So that way it knows where that is. So after you run your program, if you jump to, you would see the value there because it puts it back into the memory. Okay. After you load, you know how you set value last time when you test your lab, that's how you see it, is because it computes it, and it uses the MAR to point to where your data would be, what value you set. Okay. Any question? All right. Now, how is that compared to the LDI? Okay. For your LDI, the opcode is 1010, and so STI would be 1011. Now, the true difference is that because it's indirect, there's no PC relative mode. So instead of the address being used in the operand, like the PC offset 9, it's going to contain the address of the operand to be loaded and stored. Okay. So this is where it could be anywhere in the computer, not just within the range of the 9 bits, that what we seen in the load. Okay. And the destination register for the LDI and the source register for the STI, it's going to do the same thing, right? So ultimately, you still achieve the same thing. Okay. The only difference is in that it's not going to use the 9 bits requirement in that scope of addresses. It could be anywhere, and the address being used is going to be the operand that can be loaded and stored. So it's actually accessing the address location twice in the back. Okay. First, it points to it, then it goes and put it. Whereas this, right, it only accessing memory once. Okay. Question. Okay. So here they tried to, this diagram kind of give you a little bit more detail. So as you can see, right? So when we use the LDI, right, these units are always going to be at play because this is within the processor. So your ALU, it's still going to compute the addresses, okay? But there are two locations that are separate in an LDI. Compared to an LD, it's one location, okay? So in the LD, that's going to be within the bit 0 through 8, the PCE9 offset, that will be just one. Whereas in the LDI, two separate locations. Okay, so how does it retrieve the data? So it accesses it once to put it there, and then it's going to access it again to put it back. So that way the processor can see what value that is and which location has the value. And I hope that clarifies, right? But, you know, just from a coder or a programmer standpoint, right, you can still load and indirect from how you see the resources, they are different. Okay. Now for the LDR, that's a base offset. Okay. So LDR uses opcode 0110, and same for when you LDR at the beginning, you have to do an STR at the end. So that would be 0111. Now the base offset mode, it used the operand bits a little different. Okay. So the address of the operand is obtained by sign extended 6 bits 0 through 5 for the base register, and it would take the instruction from bit 0 through 5 and specify it in bits 6 to 8. So it would take this here and then specify that here. Okay. So that means that the 6-bit value is then treated as a negative or a 2's complement of integer between -32 and +31. So as it would then first need to be sign extended for the 16 bits before it adds the base register. Okay, so that's how it's able to identify the location of your value. Okay. And then we have used LEA at the beginning. LEA just skip. So what it does is it loads the effective address by using this opcode 11110. It loads it to the register from bit 9 to bit 11. Okay. The immediate address mode, let me see if, yeah, I do have a picture for it. So it has the PC offset similar to LD 0 through 8. That's the 9 bits, right? It would then have the address that would be very close to what was initialized. So it is closer to what you would start. Okay. So when you do like an LEAR and a certain value, it would add that value. Okay. So let me show you a little more here. So when you look at this picture, LEA is the most simplified. Okay, sign extended, go through the ALU, skip the PC. Okay, and it points directly to the location. So when you initialize the string using an LEA, basically you point to the string location for that register 0. Okay, so the register 0 would then access the address of that string to be able to load it. Question? Okay, let's do the next part in our assignment. Here's number 12. I took the picture and I put it there. So we want to put this into binary. Okay, let's do A. So for A, we are going to do a not R2, R2. Okay, so you're going to fill in the binary. A not is 1, 0, 0, 1. And then since it's a register 2, it will be 0, 1, 0. And then that's your destination register. And where is it coming from? Also register 2, so 0, 1, 0. And then the rest of this is not going to matter. Hold on 1 second. Let me check my 1 second, okay? Let me double check something real quick. Sorry. Yeah, that's what I thought. Okay. I was right. All right, so the last 5 bits or 6 bits here, it's going to put all ones because that's how it's going to understand to not look at anything here for the not. Okay, so from a binary standpoint or view, that's what you would see with that not. R2, R2. Okay, so fill in the table. Then for B, we are going to add. So we would take register 0 and add it with register 1 and put it back into register 0. So your instruction would be add R0, R0, R1. So the add, the 4 bits opcode is 0, 0, 0, 1. So fill that in. And I put here so you can see that that's an add. And since it's register 0 for the destination, we would have 0, all 0 here to represent the 3 bits for the register. Okay. And then for our source, which is register 0 again, so 0, 0, 0. And since we're adding register, this is going to be 0 for bit 4. And then the last 3 bits on the right in brown here, that will be your register 1. So that will be 0, 0, 1. There's madness to this, right? I have a purpose so you can see your binary. And it makes sense in what we talked about and what we learned in the first couple of weeks. Okay. Okay, so it would know that this is not an immediate value because of your of bit 5 here. Okay. Question. Okay, C. We are going to AND register 1 and register 2 and then put it back into register 1. So our instruction is AND R1, R1, R2. So for the AND, we're going to have 0, 1, 0, 1. That's for the AND. And since our destination register is register 1, so it will be 0, 0, 1. And our source is also register 1001. Here we're going to have a 0, and the last part on the right is going to be your other source register. That will be 010 for register 2. Okay. Register 2. Question. Then for D, we are going to add with immediate value. So we're going to take hex 5, we're going to add it to register 2, and then put the result in register 2. So for the add, the first 4-bit will be 0001. And for our register 2, that will be 010 for the next 3 bits. Then the source register is register 2, right? So that will be 010. And since this is an immediate value, bit 5 is on, so 1 there. And then the rest of this is going to represent a hex 5, so 00101, right? Because the hex 5 is equivalent to a decimal 5. And if you convert the binary, it will be 00101.
Does it matter if it's a capital X?
Nah, yeah, lowercase, uppercase. You can use either one, upper or lowercase. In the code, sometimes we use the lowercase x because it's easier to see if you have all the capital for your instructions. And then I leave you E to do on your own. So you already done an add before, right? So here you have an add, okay? And then here you put in the binary for your register, which is your destination register. So for E, we're doing a decimal 11. We're going to add it with register 2 and store the result in register 1. So here it should be your register 1 binary. Okay. And then the green part is going to be your source register, which is register 2 in green. And then you know what it needs to do when it needs to add an immediate value based on D. Then the last 5 bits here needs to represent 11 in decimal. So it'll be 281. So this bit on, skip this one, this bit on, and the rest. This is 0. So 01011. R1, R2, and then question. I see a chat. How do I figure a hex 5? Okay. So a hex 5 is equivalent to a decimal 5. Convert decimal 5 to binary. Right? Use the scale 1, 2, 4, 8. So if I do a 1 plus a 4, right? Bit 1 plus the bit 4, right? So decimal equivalent to binary. Going back to the first week, right? So you simply just convert to binary. Oh, then for the number between, okay. So this is gonna be for 11 decimal. So if you have a 1, a 2, and an 8, this is gonna be 0. And then for bit 5, it needs to say that this is a immediate value, so that has to be on. Okay, so this has to be a 1 here, and the rest of this would be representing binary for 11 decimal. Understand? So that means that you convert 11 to binary and fit it in 5 bits. Let me re-highlight this and change the color so it doesn't get confusing. All right, question. Okay, so that takes care of that. And then let's do I'll leave it on for like a little bit here, and then we'll do the last one and we'll be done. Okay, so I hope that this exercise helped you kind of visualize how that would be when we're working with the 16-bit instructions or word size instruction at the binary level and at the instruction level. And I'm a very visual learner, so if I don't like draw, put something, I would not remember. So this helped me, so I hope that you can see it, right? And it helps you remember too on the difference between, you know, an and an add and so on. Okay, but of course they have different purposes in how we would include them in our entire program. Okay. Okay. Any question regarding number 12? Okay, let's do F. So we want to write the LC3 instructions to output the result. We have register 3 is register 1 minus register 2. Okay. So I would start with a clear register. So I would clear register 2. And if you want, you can also clear the other register, right? We can do a repeat of this. And R3, hex 0, and R1, hex 0. Recall that when we end something with 0, the output is 0. Okay. So once we clear them, we can set up the 2's complement because we have to subtract whatever that's in register 2. So we would do a not R2, R2. That will be a 1's complement of R2. And then we would add the 1 to hold the sign to register 2. So by that line, we would have a negative R2. Then the question asked us to put the result in register 3. So we would do an add R3, and we would take R1 minus R2. So that will be add R1, R2, and put it back into register 3. So the destination register is always in the front, and then the source, you always have it in the back here. So by this point, you would have R3 is equal to R1 minus R2. Okay, so simply just to do this, right? If we have to clear register, we have 2 additional lines. I like to clear them because you never know that sometimes you don't want things already in there, then you can clear them. Sometimes if you already have things that are already loaded to it, then you can just keep going. You don't have to clear them. Okay, so I clear them, and then I create the 2's complement, and then I add the 2's complement with the register that it asked for to give me the subtraction. Question. You're going to see subtraction from every lab. We are going to do a division lab where we use subtraction. We are going to, you're going to have to subtract things to branch. So we have to get used to working with 2's complement. All right, more practice in LC3. For G, you have register 3 is register 1 and register 2. So we simply do an and then register 3 is storing the result, and then the sources are register 1 and register 2. And then H, we're going to do a copy register. So that is simply adding a 0 to your register. So if we want to say register 3 is the same as register 2, we would do an add. Register 3 is your destination, and then your source is register 2. And you would take register 2, you add it with a hex 0 or a decimal 0, same. All right, I is like what we talked about with clear. So if you need to initialize a register to a 0, we would use an AND that register with a hex 0 or a decimal 0. Okay, so you can keep it like this, okay? Or if you go an additional step, all that is when you add, you basically recopy it. So I don't feel like this is necessary, but if you want, you can do that. It's just an extra line. Okay, so if we clear it, your R1 is actually at 0. Okay, so we can do an AND register 1, and the source is register 1 with a hex 0 or a decimal 0. Okay. Now, like I said, if you want to recopy it, it's redundant, but you can do an add R1 with the decimal 0. Basically, you take R1 is equal to 0 and then recopy it as R1 is equal to 0. It's just still redundant. So you can clear it, that's good enough. But if you want, you can, it also means the same. Value is going to be 0 at register 1. Yeah, I put it here because this question came up from students in the past, right? They asked, well, can they add 0 to register 1? Yeah, you can. Basically, you just recopying the same thing.
That looks like H. Is that pretty much the same as H?
Yeah, it is the same as H. Copying is, yeah, anytime you copy, you add 0. Because when you add 0 to the register, right? It's the same value, right? If you add 0 to anything, the output is the same as the source. And when you put it into a different destination, basically you take that value, you recopy it to another location. Yeah. So I would clear it, and you can clear and copy, or but clear it for I. Okay. Any question regarding these little snippets to help jog your memory or give you some practice? And as we practice more, you're going to feel more comfortable doing this, right? And in about, I don't know, 6 weeks, you should be able to crank out your project. Whatever you can write in C, you can write in assembly. It's just going to be 3 times longer. Okay. Question. Okay, so let's do 13. We are going to write the instruction to load your hex 1BA to register 2 for PC mode. So we are going to do an LD. And you can choose, yeah, so you want to have register 2, and you can make any label you want. I just decide to use LB1. And when you're using a label, you got to fill it. So I have a LD R2 with the label name. And then I would fill that label with the value that it asks. Okay. So as you saw the simulator last lab, right? When you load, after you assemble your program and you put it into the simulator, you notice that it shows the fill, right? It takes up the location, like an instruction for the pseudo instruction, so it fills it. So say label 1 here, right? Label 2 before it runs. Then you can set the value. So when you set the value, it would associate that value to your label, which is an address, and it uses that address in the ALU to be able to compute and give you the output in the right location. Okay. Then for 14, we are going to load indirect. This is not a PC relative mode. So you are going to indirectly load the address hex 3048 to register 1. That's easy. We would do an LDI register 1 and a label name. So I use an LB2. And for my label, if I use a label, I gotta fill it with the address value, which it tells me here, 3048. For 15, we are going to write instruction to initialize address 3002 for label 1. I would not use it like this in a regular program because that's so close to your origination, right? You want to use like 3102 or something like that, or 3202 or 3200 further down. Okay, so this is initialize address for LB1. So we are going to do an LB1 register 0 LEA. and we are going to copy it to register 1. So why am I not doing register 1 here? I cannot. LEA uses register 0, period. Okay. So you have to, when you do an LEA, it has to be register 0 and then your label name. And then you are going to copy it to register 1 because that's what it asks. Well, it didn't say that, but if you need to use another register, you need a copy. And then you are going to fill the label. Okay. So can you continue to use register 0 as long as you don't need register 0 for other things like input, output? Okay. So yes, you can reuse that register and not have to copy it. But if you need to free up your register 0, you have to copy it. Okay. So if I need to do an input right after this, I have to copy and then do an in. And remember that for your project, right? Because sometimes you have to prompt the user something and then record an input and then move that input to another register and then free up register 0 to prompt again. And then you saw it in the lab last time. So you have to move things in order to free up that register and then use that register for other things. Okay, so that's how you can copy it real quick to free up that register. Any question on 15? All right. So 16, we are going to do something similar to what we did last lab, and I hope to walk you through something similar to it so it jogs your memory and you can get used to looking at like, you know, more complex calculations, because we will use calendar and we will use an algorithm, an equation that we can implement in our program algorithm to represent dates and time in assembly. Okay, sounds complex, but I'll explain down the line. So looking at equation for 16, this looks similar to your lab, right? And I wrote this recently, so it's no big deal. So when you look at this, the equation is negative p is equal to q plus t minus 5, right? So we need to really look at how mathematically we handle the equation inside the parentheses first, then we're gonna deal with the negatives, okay, and then combine everything. So start with your origination address. So originate at hex 3000. And I'm going to clear register 1. And you don't have to use register 1, but I don't like using register 0 at the start, because what if I need it for something for input and output? So I use register 1. I chose that instead. So I clear register 1 by doing an AND R1 hex 0. And I want to handle this first. So I'm going to start with a Q. And then I'm going to work my way outwards. So I'm going to do a load indirect with Q to register 1. Okay. So at this point, your register 1 has a Q, or loaded with the label Q. And then I'm going to clear register 2. And that's going to be for the T. So then after I clear register 2, I do AND R2 hex 0. Then I'm going to load the T label to register 2. So your register 2 has the T. Then I want to add them together as that would be in the equation. So I would do an add, and I put the result into register 2. So I would have register 2 with register 1 added. So that will be my Q and my T is going to be storing the result in register 2.
You have 3
Oh,
there.
I know. Yeah, I saw that. I must be really sleepy when I wrote this. Sometimes like my mind is sleepy and my hands just keep on going. Sorry. All right, so next we are going to clear register 3. So we clear register 3 here by doing an AND R3 R3 0. So can you clear them all at the beginning? Sure, right? You will see some lab program that I clear like 5 register at once at the beginning. But I want to track them as I go here so I can show you that you can clear as you go, or you can clear them at the beginning. That's fine too. So I clear register 3. Now I gotta handle the -5, right? So first I gotta bring in the decimal 5 because this is a math equation. So that is a decimal number and same equivalent to the hex, of course. So you would then add 5 to register 3, which was clear, and then put the result in register 3. So yeah, I was sleepy. Register 3 is decimal 5. And then we want to do the ones complement. So we're going to not register 3 because register 3 has the 5. So we're going to not it. And we can't make it negative until we add the 1. So after we not for the ones complement, we are going to do an add 1 to register 3 and put it on register 3. So at this point, your R3, your register 3 has negative decimal 5. And that's this part. Then we are going to combine now, right? We got to take care of this entire thing. So recall that where we left off, register 2 has the Q and the T added. So we would then bring that down here. And then in our last step, your -5 is in register 3. So we would take register 3, which is -5 plus your Q and T. And our result is going to be in register 3. So your R3 is equal to Q plus T minus 5, which is, P, right? But not yet, because I don't want to put that there because that's implying that the P label is there. So that's where we're at. But I want you to think about that is a positive P, okay? Okay, I'm just gonna put this here. It's just a thought. So after we have that, we need to make it a negative P because this we can store out to the register and then put it to a label, but we have to make it a 2 complement to represent the negative sign here. Okay. So the way that we handle this is register 3 has the result from Q plus T minus 5, and you simply take a 2 complement of the register 3. So we're going to not it, not R3, R3. And then after we have the ones complement, we're going to add the 1 to make it a 2 complement. So now officially R3 is going to hold the negative value, which is negative P, but we haven't make it a P until we store it to a label. Okay. So here we have negative P. And now since we load at the beginning, we got to store it back. Okay, put it back into memory. So lastly, we need to do an STI, and our result was in register 3. So take the result from register 3 and we put it into the label. And I use N_P. You can call it anything you want. You can say neg P or PN, whatever you want. Okay, so this is going to represent my negative P. And we are going to put it there. And we're going to halt. Then after we halt, we fill, right? That's the data section. So the requirement in the question doesn't have you fill at a specific location. So that will be your choice, just like how your project would be. Okay. So I'm going to fill at Q at 3100, and I want them to be together so I can set value and see in my simulator. My T is going to fill at 3101. And then my P is subsequent 3102. So can you fill it at 3200? You sure can. You can fill it at 3125 for all it matters, right? As long as you know what that is and it's not too far down, that's fine. Okay, so after I fill, I end. So do a .n, and that completes your program. And so looking at this, you say, okay, you know, takes a little bit of step to go through the subtraction. And then we have to set up the variable in what we would see in C++ as label, fill it, and then load the label, add the value, right? Subtract the value, store out the result, and that's it. And this exercise was recently added. I didn't require this in the last year, but I felt like I think we need a little bit more practice doing subtraction and, you know, like equation like this, so you can visibly see, right, each part of the equation being applied. And I hope that that helps you. Okay. And if you want, you can write it into the editor, assemble it, run it, test it with, you know, set values, and then, you know, jump to the location and look at the output and so on. So make sure that you set value before you run, and then you can jump to and look at your output. Okay. So this is very similar to what we've done last lab. And then we will do multiplication and division. So later on, we'll practice more with those. All right, any question? Okay, so that is the end of our assignment. I encourage you to read through the chapter. You have the access to the book, and also look at the notes again. Look at the instructions, maybe write little small programs so you can get more comfortable with it. And then, you know, simulate and run your program. Ultimately, also check out the lab for this week. Okay. So let me go to your class here. All right. So don't forget that you do have a quiz. It's 60 points. It's due at the end of the week. So you have until Sunday. In preparation for the quiz, right, you did your homework assignment, and you can also do a game. I use quizzes, so it's like a practice quiz. If you score the highest, you will receive an Amazon gift card. So I digitally will send that to you after Sunday. So if you rank high and you have multiple attempts. So you can use all your attempts, but take a screenshot, right, of your game result and then submit it so I can add the extra credit. And extra credit does not take effect right away, right? I implement it at the end of the semester. So for the students that let's say that did well on everything, project assignments, and maybe miss some questions on the final, I can put that toward the final, or whatever areas that you need. So I will look at that individually. And then your lab for this week, right? And your assignment is due on Sunday. So if you submit your assignment today, you don't have to worry about it, but you do have until Sunday to do that. Okay. And if you wanted to preview the lab, okay, we're going to do very similar to what we've done last week. So this, I wrote the instruction on how to go through and set. So we are going to do some absolute value, and we are going to do some comparison. Okay, so you will learn a little bit more about branching in this lab, and then we are going to set values and check our programs accordingly. Okay, so that is a screenshot for the code. I did do this orally with the students before, but I found out that they can't keep up with some of the pace if I'm going too fast, too slow, and so on. So I have a screenshot so you can use that as reference, so you don't have to follow me line by line. And then after that, we are going to assemble and test it. Okay, I'll walk you through that. Then we are going to do more comparison program. So, and then we're going to set the values. Okay, or initialize the values. Okay, so on Thursday, we'll work on our lab 4. Also want to remind you that we will not have a live session on the 15th, which is next Tuesday. I will have a pre-recorded, video for you to view. So please watch the video when you do the assignment. I'm required to be at a board meeting from 5 to 7:30 or something, and I will totally miss your class. So, you don't have to attend the Zoom session next Tuesday, but this Thursday we will do the lab together, and I'll remind you again via announcement and on Thursday. Okay. All right. Type your name into the chat if you are done. We are going to stop recording.